Okay, so today we're looking at in lesson 6 here, parallel circuits. So there's a video there on the website for you to look at bulbs in parallel. All right, so parallel, as we know, kind of means next to each other. So let's have a look at in your notes there. There's this diagram. All right, so here it is. Here's our diagram, and so in this case, we got this little charge and the conventional current. So it leaves the battery and off it heads around the circuit. Then when it gets to here, there's a decision to make, because it can't go both ways. It can't clone itself, can't split in half, so it has to go one way. Or the other way. Now, when you look at each of those pathways, so the blue one that comes up around this way, and also the green one which comes around this way, and then they're joined after and before that, of course. But you'll notice that each little charge, therefore, only goes through one of our resistances. So the energy that's given here at the EMF, in this particular case, because it's got no other bits, gets used up, can get used up in all of it in that one resistor. So this V1 and the V2 are equal with each other. So parallel means voltage equal. Now, in terms of the current, I already mentioned that it splits up, and so we've got these two bits of current, I2 and I3. And remember what Kirchhoff said before: whatever current we've got here, whatever charges we've got there, we can't have more or less in each of these two branches. So I2 and I3 that I've got, these ones here, I2 and I3, have got equal to I1. So what we know about in parallel, current adds up. Now you'll notice that that's the opposite to the series, so you've got to get that straight in your head, which is which. So in parallel, our voltages are the same and our currents add up. Alright, so that's in your notes there. And so in parallel circuit, if we've got, and then we've got a whole bunch, we could have a whole bunch of stuff here, and so on. And so our currents, when we get to here, splits up. Some goes that way, some goes this way, some goes this way, and so on. But what we know also is we know that the voltage across each of those is the same. So what do we know? Well, we know that the total current is the sum of all these currents. It's a bit of a mess. I3. So the total current is equal to the first current plus the second current plus the third current, and so on. Now ohms tells us that V equals IR, and so our total current is the total current in the whole circuit. I'll rearrange that first by dividing by the resistance, and we get V on R. And so, of course, the V is the same across all of them, and in our circuit back here, that's the same as the EMF up there in this particular case. Alright, so I can then write an expression. I can write an expression that says that the total current would be the voltage over the total resistance. So that's using this. Current 1, remembering that the voltage is the same over the resistance 1. Voltage over resistance 2, and so on. Now, because the voltage is the same across all of them, then we would say that voltage over the total resistance, I can take that out as a common factor, and then I have 1 on R1 plus 1 on R2 plus 1 on R3, and so on. Now, V goes into itself once, so what we end up with is an expression that for parallel resistances, the total, or 1 over the total resistance, is just 1 over each of the individual, and then you sum them, the sum of. Alright, so this expression tells us the equivalent resistance for parallel resistors. Now there's another video there, equivalent resistance, for you to have a look at that explains this more. Alright, so what we have is an example, and here's your example. Alright, so we're back to our Nikon wire, and it's two resistances, one of 10 and one of 20. And it says if they're connected in parallel, what is their effective resistance? So that's this expression back here. Whoops, too far. That's this one here. So 1 on the total resistance, or the effective resistance, I've got to put a T there. It's 1 on R1 plus 1 on R2 plus 1 on R3 and so on. So in this case, for part A, 1 on our total resistance, because we've got 2 of them, just that. And of course, because one of them is 10 and the other is 20, we get that. Now, if I perform a bit of mathematical magic, times that by 2, then we get 2 on 20 plus 1 on 20, which is 3 on 20. So 1 on the total resistance is 3 on 20. So also by the magic of mathematics, what we do to one side, we've got to do the other, and so what we can do is flip them around. And so that I don't have to go to the next page, I'll write it over here. So if we flip over both sides, total resistance over 1 is 20 over 3. Anything divided by 1 is just itself. And remembering in physics, we don't like fractions, we like decimals, and get your calculator, and that's 6.79. Alright, so it then says what will total current will flow through the battery, through them, and what power will be produced is the combination post a 12-volt battery. Alright, so there's a couple of things there. First of all, the the current. Alright, so current, we know ohms says that V equals IR, and so in this case we've got a 12 volt, we're talking about the whole lot, and so this is the 12 volt battery and the total resistance that we are talking about. So 12 equals the current times the total resistance, which was 6.7, divide both sides by 6.7, and you find your current is 1.8 amps. Alright, the second part of that asked about power, and power of course is VI, VI, that's better, and so the voltage was 12, current's 1.8, multiply them together and you get 21.6 watts. Okay, so that's it for lesson 6. And you've got a couple of videos. My notes, of course, are on the website there, and there are questions in your textbook.